Okay, so I guess we're gonna get started. I'm David. I'm a GSI for this course, if you don't already know that. John's going to be absent today, so I'm going to be covering this lecture, and we're going to be talking a little bit about adversarial networks. Adversarial networks are some of the coolest, kind of crazy things that came out of this deep learning era. But before we get to that, first, does anyone have any questions about logistics for the course or any kind of the upcoming midterms and other kind of components? Okay, so then last time we were talking a little bit about generative adversarial networks. GANs are a process generative model. They work with two different network components in order to first generate a proposal image. And then you have a discriminator, which discriminates whether or not that image was from the real distribution or from the generated distribution. And over time, with this two-player game, this converges to a local minimum, and we get a model of our data distribution. So these are generative models, which basically are trying to model just the data distribution as opposed to modeling any kind of conditional probabilities. They're very cool. They have a lot of potential applications from creativity to animation generation. I definitely recommend taking a look at that lecture if you haven't already. Does anyone have any kind of lingering questions from the GAN lecture before we move on? Okay. So recently, machine learning has been really quite popular just about everywhere, right? We've seen it in autonomous driving where it's used to detect people or objects in the scenes. We've seen it in healthcare where people are deciding what to use in terms of treatments. They've used it for cancer detection. They've used it even for triage in kind of dangerous scenarios. And then additionally in the smart city, we've seen a lot of AI used just about everywhere. And so one of the things that kind of comes with a lot of these applications is this problem of security and privacy, right? So there's a lot of adversaries out there. There's a lot of kind of evil people in the world who want to exploit the programming and the systems that we're using for their own benefit. Um, there's kind of a lot of different ways in which people can do this, but in terms of all of our systems, we live in this adversarial environment. There's always adversaries out there who are seeking to exploit whatever systems we develop, particularly in the AI realm. There's a lot of potential applications of things like this. Imagine if you could adjust, for example, if someone was using AI system to decide who got loans in a financial environment, or if a system was deciding to, hire or not hire people for a job, or maybe even just pass them on to the next phase. We already see this a little bit, where you can actually go in and adjust the output of these algorithms and change the output of these algorithms. So the more neural networks we use, the more there's kind of this potential for adversarial adjustment of these neural networks. Luckily, or really, I think what this slide was trying to say is that this is a nightmare. It's really a pain. And so we need to find ways to defend against all of these potential adversarial attacks. The Office of the President in 2016 basically said that adversarial machine learning is one of the key research focuses in the next world, or in the next 10 years, in the next 100 years. Because so much of this world is being devoted to algorithms and algorithmic development, we're kind of going to see a lot of potential adversaries trying to exploit this. And the big place that adversaries try and exploit, and kind of the big direct kind of contribution, is in this stationarity assumption. Traditional machine learning always assumes that the training data that you pass in is the data that's going to be used in the real world. Right? We always assume that we're trying to model the same input distribution to get the same kind of test time distribution. But it turns out, right, that there's a lot of different images. There's a lot of different things that you can put in. There's a lot of things that look like a natural image that maybe aren't a natural image, right? So if we have a particular training data set, then if our test data doesn't necessarily look like the training data, we have some serious problems. So what we can do, and one of the cool things that people have done, is they've developed systems where we can use just a little bit of adversarial noise. So we add a little bit of noise to an image. For example, we have here this picture of a panda. We add a little bit of noise, and this picture is now corrupted, right? It no longer looks to the machine learner like a natural image. It looks like something else in the data distribution. And that shows because we've moved the classification of our ImageNet model from panda to now gibbon with this little bit of noise. Notice that as a human, we can't pick up on this noise. It's almost completely imperceptible. But we've actually managed to change the output of the possible classification. And so what we're going to talk a little bit about in this lecture, and just generally maybe something to keep in mind for both the projects and generally into the future, is that there's a lot of different input options, right? For example, the computer vision project in 182, one of the things that we might consider doing is looking at this and saying, well, we have an image. What happens if we add some adversarial noise to it? And the way that we do this, and the way that we generate this adversarial noise, is through a method. This one was generated through fast gradient sign. But basically, we take the target class, and we take our noise, and we optimize our noise in order to produce gradients in the target class. And so we can do this in a lot of different ways. But this is basically some more examples on MNIST where we can kind of corrupt these images and try and get them to modify them in such a way that we can adjust the output class. Does anyone have questions on just like what an adversarial image is?
I have a question.
Yeah.
So for the project, it was saying that we needed to worry about natural perturbations. So I thought an adversarial example would not be natural.
Well, an adversarial example is maybe not necessarily a natural image, but it is a natural perturbation, right? It's one of these things that people might do, right? Things people might put into your network. And so it's the kind of thing that you should consider for the project.
Okay, thanks.
Okay, so we can see here that we have these 4s. We can add some noise to them, and they're classified as 7s. But one thing that we notice here is that we have a whole lot of noise. These are less kind of recognizable as 4s than they used to be. And so one of the things that we do is we actually penalize when we're maximizing these adversarials. So there's kind of a couple of different ways. And the big thing here is we want to take a look at this optimization formula. Here, what we're trying to do is we're trying to minimize the divergence between our original sample and our original sample plus our adversarial noise. But we want our classifier of our new sample to be this updated class. So what we're trying to do is we're trying to minimize our perturbation while maximizing the probability of our perturbation being our target class. The fast gradient sign method basically says that what we're going to do is we're going to look at the gradients. So this delta is going to be in some kind of 0, 1. It's going to be very, very small perturbations, like 1 pixel valued perturbations. And that's one of the ways that we do it is we act by creating our delta to be the gradient of the sign of the gradient. So here we're minimizing this divergence. We're trying to minimize the class score, and then we're trying to update this. And it turns out that this is really easy to do to a network. If you have access to the network and you can access the gradients, then it turns out that maximizing this objective trying to kind of visualize a fooling example like we did in assignment 1 is actually a very easy thing to do. For example, in autonomous driving, oh wait, I can clear these annotations, I think. Let's see. Does anyone know off the top of your head how to clear the annotations?
We don't actually see your annotations, at least I don't, but
Oh.
there's an erase button.
Okay, interesting.
There's
Good
also
to
a
know.
back arrow.
Yeah. Well, I guess I will deal with that in a point. So it's good to know that you can't see the annotations. And so, yeah, so basically autonomous driving is really important. And one of the big things we want to do is we want to detect the signs in an image, right? We want to know if there are stop signs, we want to know if there's speed limits, yield signs, etc. And one of the questions is, you know, how do we deal with these perturbations? There could be adversarial attacks which try and disguise these signs. In real life, you know, we can see these stop signs and it doesn't change the meaning for a human, right? We have a stop sign on the left, we have a stop sign on the right. They both look like stop signs, and no one's going to confuse the stop sign with, say, a yield sign or a do not enter sign, or say maybe something even a little bit more nefarious, such as like a speed limit 500 sign, which could cause, say, an autonomous vehicle to speed up far beyond what is a safe limit. Unfortunately, we can design methods which take this varying physical world and design systems where we can add small amounts of perturbation, small amounts of information to the stop signs, try and make some modifications to these stop signs, and eventually we get, we'll get signs that are a little bit more, sorry, I'm just going to skip through a bunch of these, I think, to get to an example. We get these signs which are a little bit more kind of very subtle in their design. For example, these ones on the left here, but actually are completely confused as something that is 100% different, right? For example, these middle stop signs, these camo graffiti signs, are actually speed limit 50 signs when neural networks kind of look at them. So let's look a little bit more closely at how we can do this. One of the kind of things that we see is that we have this varying conditions, right? We can't just look right on at the stop sign. If we want to generate these examples in the real world, we can't just make slight perturbations to the kind of pixel values that we might originally consider, right? We have varying physical conditions. We might look at the stop sign from a lot of different ways. And so it's really hard to just make varying pixel valuation changes. Indeed, while we can confuse this panda as a gibbon, we can't really necessarily just take these pixels and apply them to the real world. So we have digital noise, but we actually really want to kind of create images where we can actually apply it or generate physical outputs. So we can't do this. We can't really modify any of the backgrounds. What we can do is we can add kind of stickers or graffiti or images to the stop sign. We can do some additive modifications in order to affect a change. So originally, right, what we're trying to do is we have this perturbation, and what we're trying to do is our loss function looks something like minimize the size of the noise. This is this delta, this lambda delta, and simultaneously minimize the loss function, which classifies our input plus our noise to our adversarial target label. This is originally what we wanted to decide to do, right? And this generates noise across the entire image. But one thing we can do instead of generating noise across the entire image is we can actually restrict the noise to be generated in a very small part of the image. And the way that we do this is by adding these mask values. And so what we can say is we can say that we want to change, we want to have a perturbation in a particular area of the image and only add particular parts of the image. So imagine we have, say, we only want to add information to the stop sign. We can mask out the rest of the image and we can say, okay, if you make changes in the rest of the image using this mask value, then effectively what we're going to do is we're only going to take into account the changes you make within this mask. And this can allow us to disguise these adversarial perturbations in very specific parts of the image. Does anyone have questions on how you might disguise these and how this works?
Quick question.
Yeah.
So, what's the motivation behind using, you know, mask of a specific shape? Like, when can we just use mask of, any randomly generated shape? Because it looks like these masks represent, specific items or shapes. Like, is there a motivation behind that?
Yeah, so imagine you want to go out in the real world and you want to actually place one of these items on a stop sign, right? Uh, if we kind of just restrict them to being weird shapes, or if we just kind of pick whatever mask we want, a lot of people will recognize the fact that something's been added to the stop sign or we've defaced the stop sign. And so one of the things that we can do is we can mask this, we can hide this in something that might look relatively unassuming, right? For example, imagine you take an Apple sticker and you put it on a stop sign. No one's going to kind of think twice about that. And so this is kind of one of those things that imagine you have the sticker, you could just stick it on the sign, and it turns a stop sign for an autonomous driving vehicle into a do not enter sign. That could actually have real world effects that are kind of dangerous. Does that answer the question?
Yeah, thank you.
Other questions on this? Okay. So yeah, we have this kind of subtle poster, this camouflage sticker, and we can use it to mimic vandalism, or even just like mimic art. And it can kind of hide in plain sight. One of the big issues though with this like hiding in plain sight is that a lot of times the colors that are generated by the optimization process are actually impossible to print or impossible to fabricate. This is something that people found when they went into the real world and they tried to do these, is they basically said, well, how can we generate these images? And it turns out that the colors that were generated had to be very, very specific in order for the effects to happen. And just like changing the color just a little bit would actually move the sign back into the stop sign realm. And so what they developed, this is MPS. This is a very cool paper. They actually create some sunglasses which turn you into different people to face recognition systems. But what they did is they took a additional loss function. So they added an additional loss function to this computation where effectively they said, okay, we need to be able to print these. And so they took this additional loss that said the mask has to be printable. So they took the printable RGB triplets and they said, okay, let's make sure that the colors look like these triplets. So they sampled the set of triplets from the color space. They were able to print them and actually ended up with some very, very cool elements. Does anyone have questions on that? Okay.
So is the masking done by the person who's trying to confuse the model or the person who's trying to unconfuse the model?
So the masking is usually done by the person who's trying to confuse the model. Mostly because what you want to do is you want this masking to kind of hide in the real world. And generally this generation should hide in the real world. And so you want both a human to look at it and be like, well, nothing looks funny here, but you also want the model to look at it and say, this is something completely different from what it is. Okay. So how do you evaluate these? Well, one of the things that you can do is you can do lab tests, right? You can take your camera and you can look at your road sign or your adversarial example from lots of different angles and lots of different spaces, and see what the classification performance is. Another one is that people will actually do driving tests where they'll take a car and they'll drive through and they'll record a video. They'll sample this video and then they'll run the sampled frames through the DNN, trying to evaluate their stickers. And we can see that the target class here is a speed limit 45 sign. These are some of the generated models or generated examples using these masked and triplet based losses. Most of these look pretty much like normal stop sign. Nobody would really think anything's particularly amiss here. For example, they constrained these models to be within the mask. For example, this middle, they have this mask, which is like love and hate. And then they also constrained the RGB to be within the black and white color sphere. And we can see that on the left is the perturbed sign, and on the right is the actual sign. And these things actually tend to work in practice. You can see the classification down on the bottom. If you pay attention to the stop sign, you have this perturbed element, and you can see that it's actually changing the perception. Another example, this is the slightly otherwise perturbed. You can notice that here the perturbation is even more, whoops, I can't just replay the slide, it seems. In the second one, the perturbation is a little bit more subtle even. You can't even see the full perturbation in this video. Similarly, we can add attacks, these physical attacks, and notice that the stop sign is no longer classified as a stop sign, but as a set of bottles in terms of object detection. And so you can run these detection attacks against a lot of different methods and a lot of different things. So it's not just classification models where you can run these adversarial attacks against. It's also, say, object detectors. For example, nobody detects a sign there until it gets very, very close to the image. It just detects bottles and people. So these adversarial perturbations are possible in the real world, and they can hold up under different conditions, viewpoints, and distances and angles. Does anyone have questions on just like generally adversarial examples or motivating adversarial examples?
May I ask a quick question?
Yeah.
So is it possible, like have someone tried to design an architecture in which we can detect whether or not something has been perturbed?
Yes. So this is one of the things, and I think we'll talk a little bit about defenses later in the lecture, but a lot of people are trying to detect whether or not something's been perturbed and then also defend against perturbations. This is kind of one of the big things that we do as adversarial example researchers, is trying to determine how can we make our models robust to these adversarial examples, and then how can we detect if something's been adversarially perturbed.
I see. Thanks.
So we've talked a lot about this kind of classical formulation, right? These different approaches that we need to optimize the objective. One of the ways is, of course, just directly optimizing this loss function. This can be kind of slow, just because it might take a lot of steps to converge. And so one of the ways, one of the ways that we can kind of do this is take a more quick approach. This is what's called the fast gradient sign method. And when we update, we actually just update based on the sign of the gradients. So our update rule isn't the full gradient update rule, like fast gradient, where basically we have our B is our learning rate in this case. So our optimized is our X plus our learning rate times the sign of the gradients of our class with respect to the target value. In the fast gradient method, we're just normalizing the gradients by the magnitude of the gradients. This is very similar to the things we've seen before. However, in the fast gradient sine, we actually can just take the sine of those gradients, and it turns out that the sine of those gradients is actually very, very easy to do. And it works particularly well. So it's both quick and efficient, and it optimizes this objective. And of course, we can also use these iterative approaches, right? We can use SGG, Atom, or any kind of optimizer. But one of the real issues with all of these methods is they require knowing the model that we're trying to optimize against, right? We need to know all of the model weights and all of the parameters and all of these things about the model. These are what are called white box attacks, and they require a lot of information that in the real world we may not necessarily have, right? You might think, oh, well, no one's ever going to have access to the weights, so this isn't a problem. But actually, there are ways to do black box attacks. Black box attacks are a different set of attacks where we don't have access to the model. All we have is either access to no model whatsoever in terms of a zero query attack, or we can query the model, but we can't get any information about the gradients. In zero query attacks, which are kind of the scariest of the attack phases, one of the things we can do is we can randomly perturb our input and we can see what happens. What that allows us to do is basically randomly estimate what the gradients are. If we don't have any query, then we can try and just like randomly perturb it and hope that it works. Another thing we can do is probably more reasonable in terms of a zero query attack, where we actually attack a different system. So we do a white box attack against a system that we think is somewhat similar, and then we hope that it transfers between the similar system to our new attack phase, or our new model that we're trying to attack. If we have query access, everything becomes a little bit easier. One thing you can do is you can do finite differencing. So basically, you can perturb the image in two known ways and try and estimate the gradients just by doing finite differences. And basically what we can do is we can make lots and lots and lots of queries against the system to try and estimate and determine what changes we have to make in order to update the model. So this is relatively effective. When you have a query-based attack, you can actually get very similar effectiveness to a white box attack. When you're doing zero query attacks, it's a little bit more difficult. Does anyone have questions on the difference between white box and black box and the difference between zero query attacks and query-based attacks? Okay. So living in this realm of zero query, you might ask how transferable actually are these models, right? If we have adversarial examples, how transferable are they? So some people did some research on this, and what we actually found is that it turns out adversarial examples are relatively transferable even across different methods. So if we look at this left matrix here, we can basically see what the source machine learning technique is, and that is the adversarial model that we're using to generate our zero query attack. And then the target is the model that we're trying to fool. And we can see on the diagonal, right, these DNNs. On the diagonal, basically, you're using the same kind of model to fool the same kind of model. And we actually get pretty high performance. With the exception of k-nearest neighbors and deep neural networks, all of these methods are relatively susceptible to fooling attacks by the same kind of model. But one thing that is a little bit more surprising is that these methods are actually foolable by other kinds of models. For example, we can use linear regression to fool SVMs pretty effectively. So a fooling example generated with linear regression or a linear regression model actually can fool an SVM-based model 91% of the time, which can be kind of scary, right? We don't ever necessarily have to have attacks or directly model the system. We can actually fool the model directly. If we look at DNNs, we have the same matrix where we have 5 different sources and 5 different target deep neural networks. Of course, on the diagonal, these methods are much, much better at fooling. We can see that if we have the same deep neural network, right, if we're performing a white box attack, we actually get better accuracies. But it turns out that even off diagonal, even about 60%, between 50 and 60% of the fooling examples still fool other deep neural networks. This means that these models can be, or these attack fooling examples can be relatively transferable. One thing to note here, though, is that we have this sixth column in this matrix on the left, and this is an ensemble. We can see that for the ensemble, actually trying to fool the ensemble using any of these methods is actually very difficult. And so one of the things you can do in order to defend against black box or even white box attacks is train ensembles of models. This means that a perturbation which maybe fools one model won't necessarily fool another model. This is one of the more effective techniques. Does anyone have questions on transferability? Okay. So let's move on to, there's kind of two things that we might want to try and do, right? We might want to fool a example to be, just anything else besides the target. Or we might try and fool the target to be an exact sample or an exact target label. This is the difference between a targeted versus a non-targeted attack. Non-targeted attacks are designed to just confuse the network. They don't really care what the target label is. They basically just try and mislead the network. Whereas targeted examples are trying to mislead the classifier to predict an exact label. So basically, if we want to perturb a stop sign to be a do not enter, then that would be more a targeted attack. Whereas if we just want to perturb the stop sign into anything that's not a stop sign, that would be a non-targeted sample or attack. So the ground truth, here's just an example here. Of targeted or non-targeted attacks. And it turns out this non-targeted attack, the ground truth is a running shoe, but actually the non-targeted attack can generate lots of different samples amongst all kinds of different models. It's transferable. This one in particular is transferable across lots of different state-of-the-art networks, and they're all kind of perturbed to be different. So these non-targeted examples can be much, much better used in transferability, whereas targeted examples have very, very low transferability. This is one of the things that we've seen kind of consistently, is that when we do targeted adversarial perturbation, we have very, very low success if we're doing white box attacks against a particular model and trying to transfer them to other models. So training an ensemble of models, for example, might be far more effective a defense against targeted attacks than it would be against non-targeted attacks. Does anyone have questions on that?
Wait, just a quick clarification about the table.
Yeah.
So what does the number in the off diagonals mean again?
Okay, so what this means is the percentage of fooling examples. So basically we train on the model on the left, and we evaluate the examples on the model in the columns. And we say, okay, how many of the generated fooling examples fool the target model? So on the diagonal, we have 100%. That means that they're perfectly adversarial fooling examples when generated on the same model as that they're evaluated on. But off diagonal, we're only fooling with about 2% of these generated samples, which means that basically, if we use a VGG16 to generate fooling examples for, say, a ResNet 50, only about 2% of those examples will actually achieve the target class.
So are all the entries in this table black box attack?
These are all white box attacks.
Oh, okay, I see. That makes sense. Thanks.
Yeah. Any other questions on this? Okay. So how do we do these black box attacks based on transferability if they're really bad at generating targeted examples? One way is that an adversary might train a white box model to generate adversarial examples and transfer to this black box system. That's what we've kind of seen so far, is we'll basically use a white box model, we'll generate an adversarial example and transfer it to the system. Another way is actually using ensemble targeted black box attacks. What the adversary does is they basically train tons and tons and tons of white box models, and they generate adversarial examples that fool all of them. And so basically by adding more models, they can try and guess at the structure of the black box system and try and achieve everything in a single adversarial example. Does that make sense? So
Wait, sorry, quick question. So if the off-diagonal entries in the previous table are all pretty small, then how is it, how hard is it to train something that can fool all the white box models in parallel? It seems like a pretty hard task.
Yeah, it's a relatively difficult task. And because this is a joint optimization, actually what it is it's not so much that it's a difficult task to optimize, but what it really is that it's difficult to get these targeted examples to play nice with the black box system that we're training on. So what we have to do is we need to capture enough of the parameter space or enough of the structure of the model in our white box models in order to generate adversarial examples that are going to transfer.
Okay.
And we can see that generally it's really hard to do this, right? If we're trying to do a zero query attack against a black box system, a zero query targeted attack against a black box system, it's very difficult to do in practice. But one of the things that has been done, if we look at this, is we can actually use these zero query black box attacks to attack online systems. So the ground truth is Broom. The goal is to attack to this weird bird. And we can get close, but we can't necessarily, with these adversarial or these white box attacks, actually get the exact class that we're looking for. Notice that we can see that this adversarial attack generated with these ensembles can produce, bird-like things, feather-like things, flora, but it doesn't produce the exact class. Here we have a water buffalo. We're trying to produce a rugby ball. And actually here we get a little bit closer. We get balls, sport, games. But notice that the adversarial perturbation, the magnitude of the perturbation is much, much higher on these attacks. So even if you have query limited attacks, you actually are running into issues where you can still be susceptible to these problems. Here we have yet another fun example. We're trying to transform these berries into a stupa. And actually we get pretty close. And sometimes, and I think maybe one of the things that we see a little bit more often with these attacks, when we don't necessarily care about the amount of noise, is we see a lot more kind of deep dream style features, which means that we're really adding high frequency noise to this image in order to basically change the dominating class. Humans kind of can't perceive this noise, or we kind of filter this out, whereas the model sees very, very distinct shapes. And of course, the more that we kind of perturb the image, the more clear these shapes become. Does anyone have questions on that?
I have a question about the frequency comment.
Yeah.
So if humans are able to filter out high frequency, why can't the discriminator or the neural network just blur the image to some way so that the high frequency it's basically purged from the image?
Yeah, and so that's definitely an interesting idea in terms of defenses. One of the things that people will do in order to defend against these things is to make transformations to the image, for example, blurring. And what that does is it removes some of these artifacts that can cause kind of really crazy classifications. So in the real world, perhaps blurring the image actually adds to the defense. Yeah. Any other questions about this? Comments? Thoughts? Okay. So another time, so we talked about these zero query attacks. They're really fun. But we can also do query-based attacks. So imagine we have an infinite number of queries against the model. What are we going to do about this? One of the things we can do is we can do finite differencing. So basically, we actually go out and we compute estimates of the gradients. So we make two different perturbations. We can make a positive perturbation and a negative perturbation. And we can actually try and determine what the gradient is by taking the difference of them and dividing by the size of the perturbation. And what that gives you is that gives you an estimate of the gradients at any particular point. So we can kind of take this, we can do the finite difference, and then we can update our adversarial example with these finite difference estimated gradients. And what that allows us to do is basically allows us to attack a system without actually having access to the gradient parameters, but just by estimating the gradients instead. For samples like images, though, this can be really difficult, right? If we have very, very high dimensional inputs, we actually have to make finite differencing work across all of these all of these dimensions, right? We have to make an estimate in all of these dimensions, which can have very, very complicated, very, very difficult interactions. And so one thing we can do is we can reduce the number of queries necessary by grouping the parameters using either random grouping or PCA and doing finite differencing on these groups of parameters. And it turns out that this can work. And effectively, this can actually work very, very well. There's a lot of different ways that we can do these attacks. For example, we can see here that the white box attacks are actually very effective, as would be expected. But the finite differencing attacks are actually fairly good. And if we use the random perturbation, not necessarily the random perturbation, but if we use the PCA groupings of the methods or the parameters, then we can actually get very, very good estimates or very good adversarial success with just finite differencing methods. For example, on a ResNet, we can see this as well. Notice that random perturbation is actually still very effective. So if our steps are, if we use like 32, if we use like very high variance, we can actually just randomly perturb the inputs. Like if we don't care too much about what we want the output to be, or what we want the model to look like going in, we can actually do a pretty good job at confusing the model just with randomly perturbed inputs. Does anyone have questions on this?
For the adversarial score, are these
Yeah.
just like a percentage of the full images of succeeded?
Yeah, so this is the percentage of successful fooling examples. So what they do is they generate about 100 examples, and then they will check to see what the success percentage is of that set of examples.
Well, then that will require like the same amount of examples for each method.
Yes. So you generate the same number of examples, but the problem is these methods aren't always successful, right? These attacks aren't always successful. You can try and optimize your gradients out, but you may not necessarily be able to optimize to a point where the model is entirely unable to defend against them.
Mm-hmm.
Other questions?
Can you explain again why reducing query size is helpful?
Yeah, so one of the things is that you have very, very high dimensional inputs, right? An image is, for example, 256 by 256 by 3. That's a lot of input dimensions that you have to do finite differencing against, right? So what you really want to do is you want to do feature groupings in such a way that you can reduce the number of samples or like the number of finite differencing steps that you have to do when you're querying the system, right? Because if you make a query for every single one of those input dimensions, someone might get, that might set off alarm bells, for example, right? If you're making, millions and millions of queries against a system. So the goal is to reduce the number of queries that are necessary in finite differencing. And the way you can do that is by grouping the features or by grouping the input dimensions. Does that make sense?
Yes, thank you.
Okay. So basically, we can see that these finite differencing methods with these grouped query reductions can actually perform pretty similarly with gradient estimation black box attacks. Okay, so you see we can do this. We can basically transform images that are not safe into images that are considered safe. This can be a real issue. A lot of people are moving towards automated content moderation, for example, in online systems. And so one of the things that adversarial noise can do is it can perturb perhaps a not safe example into examples that are particularly or are classified as safe. And so you can get images past an online content moderator by adding adversarial noise without actually having issues with the content moderation. So this is one of those attack vectors that you could actually see in the real world, is trying to determine what's safe and actually viable versus what's not. I don't know if anyone's done a black box attack against the YouTube content moderation algorithm, but that would be a very interesting research paper. Okay, so black box attacks, they're possible on deep neural networks with query access, but we want to be able to reduce the number of queries. One way to do this, or we've talked a little bit about finite differencing, but another interesting or possible method is using GANs. And the interesting thing about a GAN is that it has this ability to generate examples and then be penalized for generating the examples. So there's a couple of different ways to do this. One, if we're making a white box attack with a GAN, we can have our original instance, we pass it through a generator, and we add that original instance to the perturbed noise. And then we say, the discriminator says, is this a real image or a perturbed image? And then we also have this loss on the second part. Imagine it's a white box attack. We have a direct loss that we can use in order to update the class in a particular direction. And what these GAN generators do is they generate samples that are very, very indistinguishable from the original distribution, while simultaneously performing adversarial attack. Does anyone have questions about how to do this in a white box attack?
What does the module on the top does?
Yeah, so the discriminator tries to determine if your perturbed instance comes from the real data distribution or it comes from a generated data distribution, just like in the GAN lecture yesterday or on Tuesday. And so the idea is you want to fool the discriminator. So what you do is you have this gradient which says, okay, we want to maximize the probability of the discriminator being fooled, right? And then we simultaneously also want to maximize the probability of this sample fooling our class. And this whole thing is differentiable, right? Which gives us this really nice balance, or this really, really awesome ability to train this on data.
Thanks.
Yeah. So imagine we want to use this in a black box attack. We can't necessarily do that, but what we can do is we can actually do model distillation and try and do model distillation from this black box attack. So what we do, I don't know if we've kind of fully covered model distillation, but the idea is you take a new model and you take an old model and you pass input samples through both models, and you try and teach the new model or the student model to predict the output of the teacher model. So basically, you're trying to train a new model to be like a, say, black box model or a teacher model. And so what you can do is you can distill a query in a query-based attack, right? In a query-based black box attack, you can distill your black box system into a model that actually has gradients. And then you can use those gradients in order to generate adversarial examples using these GANs. Does anyone have questions on that? Okay, and so in MNIST, we actually have some pretty convincing adversarial examples using these GAN-based images. So the original images are on the diagonal, and the target class is on the off diagonal. And we can see that we can perturb these images without actually doing that kind of normal, kind of weird colored noise, or the kind of ghost images, with the exception of some of these fours, which are a little bit more difficult to see. We can actually see that, for example, in the ones, it's very easy to perturb these samples in such a way that humans aren't fooled, but the network can be extremely fooled. If we do a black box attack, things get a little bit messier. But we can see that the distillation process has actually worked, and these targeted examples are actually doing a pretty good job of being indistinguishable. Now, this doesn't extend to just MNIST. We can also make these attacks on CIFAR. And we can see that in the white box setting, our generated images are actually pretty good. We still have a lot of artifacts in these images, which might be a little bit recognizable. But as far as GANs go, if you're doing these semi-white box or these black box attacks, it's actually pretty good at perturbing these images in such a way that we still remain somewhat within the data distribution. Finally, we can look at doing this actually with ImageNet. And if you look at this with ImageNet, you actually have a little bit more high resolution data. You have a little bit more data overall. And we can see that the perturbed classes are actually very good, right? You don't see the kind of telltale noise so much. Maybe in some of the Poodle examples, you can see a little bit of that classification noise. But you actually get pretty good examples by using GANs. Similarly, we can make targeted examples. And these are fairly indistinguishable, even to the human eye. It can be very, very hard to determine what the perturbation made has been. Any questions about this method?
So quick question. Are there any theories about why neural network is susceptible to perturbations like this?
Right. So the big reason that neural networks are susceptible to these perturbations is because the training time distribution is very different from the testing time distribution. And so what's happening is that while neural networks and generally all machine learners assume that the neural network, the training time distribution is the same as the testing time distribution. And the problem is that at training time, these neural networks are all receiving natural images. But the actual input space is far larger than the space of natural images. The actual input space is the pixel space, right? So not all combinations of pixels are corresponding to a natural image. In fact, very, very few of them are. Natural images are probably infinitely outnumbered by the possible pixel combinations. And so the issue with that is that you never see data from lots of the pixel space where you kind of don't necessarily make the right predictions because you've been focusing on this natural image space. And so that's kind of the big question there. Does that make sense?
Yeah, but I think for humans like us, we learn how to classify objects based on natural images. But even when we look at adversarial images, we are not necessarily fooled unless they're drastically perturbed. Like,
Yes.
so what is the reason behind like neural network not being able to do that, even though we like are able to do it on natural image, learn from natural image, and able to distinguish, like classify correctly on perturbed images?
Yeah, I think the real issue, and maybe I don't really know. I think the real issue is that neural networks are not humans. Humans have this remarkable ability to learn and have actually a lot of different. They use a lot of different tools in order to determine whether or not something's a natural image or maybe not a natural image, or a lot of different things that neural networks don't have access to. And what those things are, I'm not entirely certain. If I knew all of these things, I would be a very famous computer scientist.
I think there's also, I see. Thanks for the response. I think there's a question from the chat.
Yeah, no, also there's a question from the chat, which basically says, will this problem be mitigated if the model is trained on adversarial perturbations? Yes, to an extent. One of the things that we can see is that these models are actually more robust if you train them on adversarial perturbations. But the fact of the matter is that this pixel space is so large that you actually can't cover all of the adversarial examples. Not only that, it's really time consuming to generate these adversarial examples during training, which means that you can't possibly cover like the volume of data required for all adversarial example sets. But one of the big ways to do this kind of defense against adversarial examples is to do things like averaging, or using the discriminator that you've been using this whole time. And so basically what we'll see is that if we use the discriminator in order to determine whether or not something's an adversarial example, you can actually improve the defense against this. Similarly, training ensembles. Ensembles are also very effective at mitigating adversarial attacks. And then this averaging, like if you're trying to do adversarials, then the adversarials can also help mitigate. There's a question from the chat as well. Is there any cross research happening between cognitive human optical illusions and adversarial examples? I don't know for sure. I think that's probably a good question for Alyosha, who does a lot of work here with adversarial examples and fooling examples, and he absolutely loves optical illusions. But I think that probably some people have looked a little bit at doing things like that. I don't know if I've ever seen someone feed an Escher painting to a deep neural network, but that would be kind of cool. I'd love to see that experiment. Let's see. Also, are there any examples in research on adversarial attacks in NLP? Yeah, there are. Not so much in terms of NLP, mostly because the attacks are a little bit harder to do in terms of like being subtle. But we'll look at a couple of different things later in the lecture, and in terms of different domains. But yeah, so basically, one of the ways that you can kind of do this is when you're defending using ensembles, or if you're defending using other methods, it turns out that these adversarial examples or these scans are doing very, very well at defeating these these defenses. Yeah, so a lot of the work has kind of focused on image classification, where the target model is known. So far, we've talked a little bit about kind of all of these other black box attacks. We've talked a little bit about adversarial methods, but also we want to talk a little bit about maybe other domains where adversarial examples could be applied. One of those domains is we can actually attack generative models. There's two parts of a generative model, like a VAE, right? There's an encoder, which maps to a latent representation, and a decoder, which maps the latent representation back to the high dimensional reconstruction. We can actually attack the hidden space in order to generate, when we decode, or generate encodings, which when decoded are completely different from the input. So basically what we do is we have an attacker which generates compression into this hidden space, right? This latent dimensional space. And then we want to target it so that the decompression method or the decoder predicts a particular example. This could be really bad, for example, if we're using a deep neural network in order to compress images. Imagine if you compress an image down or a file down using your deep neural network, and then when you uncompress it, it uncompresses into a virus. That's kind of a crazy example, but you could kind of consider that where you can make these kind of generative model attacks actually be really useful. And so we can actually generate adversarial examples, untargeted adversarial examples for the VAE GAN and MNIST. Here we have the original images and the reconstruction of the original. So we can see that our compression method's actually working pretty well. The target image is 0. And so we can have some adversarial examples that look a little bit like this. And when we decompress these adversarial examples, we get all zeros. So these generative methods are actually very attackable, even with just a little bit of data. I think this is very cool. Similarly, we can do this target attack with more complicated visual samples, things like SVHN. Or we can do it with faces. This is the large face database, I think. And we can make small perturbations to face images that will all decompress into the same target image, which is a very interesting attack. Does anyone have questions on this kind of attack, attacks for generative models?
Oh, just a quick question. So where is the attack module? Like where is the attack module placed in this structure?
Yeah, so the attack is basically happening on the compression side. So what you're trying to do is you're trying to generate an image that when both compressed and then decompressed is the target image. So basically we have a normal image that looks like a 7. We want to add some noise to the 7 so that then when we pass it through the compression module, it generates a hidden state, which will decompress to a target class.
I see, but the attacker is not integrated into the compression network.
Right, so the attacker isn't integrated in the compression. They're attacking the whole GAN.
Okay, I
or
see.
The whole generative model.
I see, thanks.
Okay, so VAE-like models are vulnerable. We also have VQA models. We've talked a little bit about visual question answering. This could be another possible kind of model to attack, right? We want to make some perturbation to the image, which changes the output class. So basically, we add a small delta perturbation to the image, and we want to change the answer to a particular question. So one particular example is, where's the plane? In this case, our VQA model is predicting the runway. We can add a little bit of noise to this image, a very small amount of imperceptible noise. And we want to target a particular answer. And we can actually do this. So we can attack a VQA model as well by adding imperceptible noise to the image. Here's another example. How many cats are there? We can perturb the VQA model using very imperceptible noise in order to generate a 2 value. This is really interesting. A lot of systems are moving towards using person counters in order to determine how many people are entering and exiting spaces. So you can imagine like wearing or having an umbrella, which counts for 100 people, or maybe an umbrella that returns 0 people. So you could see this kind of playing out in terms of actual real world implications when you have VQA systems or object detection systems in the real world. Does anyone have questions on attacking VQA or just interesting thoughts on attacking VQA? Okay, and we'll move on to one more example. We can actually attack reinforcement learners as well. One thing that you want to do is reinforcement learners are designed to take an input image or an input state and pass it through a policy network or a value function in order to determine what the value is of taking a particular action. whether it's like in the case of moving up or moving down, we can actually attack these networks with noise in our input image. For example, here we have the original frames where the model is actually performing relatively well at playing Pong. It's able to beat the computer, but we can add an adversarial perturbation into every frame in order to attack the value function of the actions in order to cause the model to actually perform something completely different. So this is actually a policy network attack where we're attacking a policy gradients-based method. We can actually directly attack a value-based method like DQN as well. So the adversarial projection here is injected only into every 10 frames. And so what this allows us to do is make very small perturbations to the input, not even particularly frequently, and we can still achieve very kind of effective results in attacking agents or attacking value functions. So the takeaway here is that reinforcement learning systems are also vulnerable to adversarial examples. To attack reinforcement learning systems, they don't even have to be injected every frame. We can kind of just directly attack these systems. So I have questions on injecting adversarial examples into RL.
How exactly do they inject the perturbations?
Yeah, so the adversarial perturbation is injected via the frame. So you have a small visual delta in the actual frame or the state space, which can lead to change in the value function.
So human wouldn't see the difference in the frame.
Right. I can't see the difference in these frames. Yeah, I can't see the difference. Maybe maybe you guys can.
No, I can't either.
Any other questions on this?
You said in addition to value perturbation, there's policy perturbations.
Yes.
Is that also by just doing stuff in the frame?
Yes, that is also just by directly attacking the frame.
So how are they? I'm kind of confused what the difference is in the two methods.
Right. So what it comes down to is we'll kind of talk a lot about this when we get to RL kind of later in the semester, but there's two ways of training reinforcement learning agents, or two really big ways of training reinforcement learning agents. One is policy-based methods, where you actually train the network to directly predict the action that's going to be taken from the state. So basically you predict the state and then you predict the action for that state. And then there's value-based methods where instead of predicting the action that you take, you predict the value of every action, and then you take the highest value. So there's a bit of a subtle difference between the two, and we'll get to that a little bit later in the semester.
Well, I have a quick comment on that.
Yeah.
Because I don't, these examples are pretty like striking, but these are technically like vision based, right? So your agent is still looking at pixels and frames.
Yeah.
And arguing that like the perturbation will work on RL, this argument is basically just saying it's still a vision problem. The vision
Right.
is not good enough.
And so, I mean, one of the things is it's easy to attack visual systems. The fact of the matter is that you could perform an attack on any state space. So you can imagine maybe making small alterations to the velocity of the ball, which could cause issues with the RL agent. It's kind of hard to directly say, okay, just throw out the vision completely, mostly because the vision very much exaggerates this problem. If you have very few things to attack, right? If you have very small input space, these attacks actually become much less effective. So trying to introduce kind of noise in the middle or trying to introduce discontinuities in the middle, like NLP, for example, where you actually have to make a decision about a word, and making decisions about this word really kind of change the whole distribution or the whole meaning. Things like this kind of are less useful in the real world because they don't necessarily have the same implications. Yeah.
May I ask a follow-up question to that?
Yeah.
So when you mentioned something like changing the speed of the ball, and which will have a negative effect on the learned policy. Like, to me, doesn't that sound more like a generalization problem rather than,
Right.
an adversarial issue? I mean, I think in general, like, is is a model that's more general able to, like, more capable of dealing with noise
Yeah.
and perturbations?
Yeah, precisely. So it really is, adversarial examples are generalization problems. That's what they are. Is overall, we kind of look at these models and we say, well, they're not generalizing to this part of the state space, which means that we can exploit this non-generalization in order to get effects that we want. If you had a perfectly generalizable model, right? So if you had a model that took every image in pixel space and correctly classified it, there would be no adversarial examples, right? And so what we're trying to do is we're trying to exploit the fact that we are not training on the full input space or the full input distribution in order to basically change the meaning of the outputs. So you could kind of think about this in NLP as perhaps maybe we always train on English, but maybe we allow the full set of Unicode characters as input to our model. So what happens if we put emojis into our model, right? If that doesn't crash the system, maybe that's something that the model has never seen before or never handled before, and it can change the output.
I see. Thanks.
But yeah, so that's generally the system. And that's kind of what we're going to talk about in terms of adversarial examples today. The big defenses that we have kind of run into across the whole thing are both using GANs, so using the discriminator to try and determine what, or if there is a domain shift at all, and then also using ensembles of different kinds of models in order to protect against them. Data augmentation and improving generalization are other very, very good ways of defending against adversarial examples, right? The better your model is, the fewer adversarial examples exist. And that's what we're going to be kind of working on in terms of the Vision project, and generally in terms of the other projects, the NLP project, and maybe even to a lesser extent the RL project, is there's a lot of different parts of the state space that you might not necessarily be training on. For example, in the Vision project, maybe you're not training on adversarial examples, or maybe you're not training on, examples that are rotated 180 degrees, right? Upside down examples. Those are the kinds of things that you see in the real world that can cause adversarial behavior. And the goal is to improve the robustness, improve the generalization across these adversarial behaviors. Does anyone have questions on the lecture from today, or just generally on adversarial examples or projects or anything?
I have a comment on
Yeah.
these kind of research problems.
Yeah.
Like, these are interesting problems, but aren't these works sort of enabling attackers or the bad guys out there to have more these tool sets, even if they didn't even, it's like these are really good bad ideas, they're really good attacking ideas, and the bad guys might not even be there yet. But these people publishing these papers are kind of enabling them to do so. And they'll be like, oh hey, there's this free paper, free so probably source code, and I can just download that and use that against some like commercial models or something.
Yeah, I think the general consensus amongst security researchers is it's better to have problems that we know about than problems that we don't know about. You see this a lot with vulnerability reporting in terms of general security, where people will report problems, for example, the Spectre and Meltdown problems in CPU architecture. It's very, very unlikely that hackers or generally people are able to directly exploit these systems, but just knowing about them means that hardware manufacturers and researchers can take steps to mitigate them. And so I think generally the expected practice is that if we can figure it out, then someone else can figure this out. And so it's best that we know about it. But yeah, I mean, that's definitely a conversation to have and to keep in mind. OpenAI last year was like, well, we're not going to open source our language model because we're afraid it's going to be used in dangerous kind of bad ways. And it turns out that by not open sourcing it, they just had a whole bunch of other people rebuild it and regenerate it. And it kind of, their fears never really came to pass. And so that's definitely something to look at. Maybe as an example of this is OpenAI's approach to it with their GPT-2 language model.
Mhm.
Other thoughts on that, or questions on the lecture?
Okay, so another question about adversarial and generalization. So so is there any potential, because okay, let me put it this way. So there's some recent work on self-supervision,
Mhm.
and it seems like they're able to capture a much bigger space with fewer less amount of data. So do you think that could help mitigate uh, some of these problems?
Yeah, I think that's definitely a potential. I'm not entirely certain it will completely mitigate the problems, mostly because a lot of the self-supervision work is based in purely natural images, right? Or in natural domain spaces. There's not a lot of self-supervision with, just pixel space images. And there's also this kind of question of, what is the right answer for a pixel space image? If you just give someone a bunch of noise or a bunch of randomly generated noise and you tell it to put it in one of the 1,000 classes, that's a really hard answer. So basically, one of the questions is maybe we should introduce something like an other class or some like extra out of domain class or something that we should be looking at. This is kind of one of those things that researchers have thought about and then not figured out how to do properly, is this like idea of having this doesn't fall within the problem parameters question. And so there's a lot of research going on right now about how to determine whether or not an image is in domain or out of domain, which would really help with this adversarial robustness problem.
Wait, but as humans, when we look at a perturbed image, we still consider that an in-domain image, even though we can see
Right.
some like ripple, we can see some effects like the deep dream effects, but we still,
Right.
when we look at the image, we still can tell that that's a berry, even though we can see these weird noises. So
Right.
like,
I think, well, one is our image space is a little bit larger, right? Our ability to learn is a little bit far more effective and far less limited than a DNN. And then similarly, basically, when we look at images, we have a much better grasp of the set of domains. If someone gives us a completely random noise image and tells us, is this a cat or a dog? Humans will likely make very similar errors, right? So basically, it's the magnitude of perturbation. It has to be much larger for a human than it has to be for a deep neural network right now.
I see. I think there's some works by Michael Cheng, which is a PhD in Sergey's lab, on generalizing like objects. So like basically like his approach is that, I mean, his not approach, his understanding in one of his recent paper is that we humans build models like in like internal models about what a berry should look like. So instead of looking at the raw observation of it, like we'll look at the image and then we'll see, okay, does this look like a berry based on my understanding of what berry should look like, instead of just looking at the raw pixel and trying to decide whether or not like the curves and the shape of the instance. So do you think that could be a helpful approach in mitigating this adversarial problem?
Yeah, definitely. I think that switching or moving towards model-based representations is a perfectly reasonable and perhaps really interesting way to do it. Model-based representations also allow for zero-shot and low-shot learning, which is a very interesting field of research additionally. I don't know if we're going to have a lecture on that. I hope that we do, but it would be very cool to talk a little bit about how zero shot and one shot and K shot, like very small data problems, can be solved with model-based representations.
I see. Thanks a lot.
Yeah. Well, with that, I'm going to bring this lecture to a close. Thanks everyone for joining us, and thanks for all of the people who are watching online later. Have a good day.
Thank you.
Thank you.